No, I have other options.
What kind of car do you have? Can you even drive yet?
Yes.
Your cars are falling
She could
apart.
drive before like all of us.
Yeah.
I lose track of how old some of you are. I don't know.
I'm-
60, I know it's
I'm an
60,
elder.
50,
Taylor
60,
and I are the
70.
youngest.
I lose track
They're
too.
babies.
Okay. Alright, so let's do this problem together.
Do we have that?
No.
Which one's that?
I know you hate this, but it is what it is. Here, wait, I can zoom in one more.
Yeah.
Alright.
Shit.
No,
I always lost a contract with you.
Alright. So,
You need a manual on. Doesn't have
I
a.
love mowing lawns.
You go like like circles like that.
I can't stand it.
Are you not supposed to go in circles?
I see you going like this way, like going across the lawn. They go to like towards a tree, and they go to follow the squirrel.
No.
She's got
Alright.
headphones, just listening to
Okay.
music, drive it all around.
So here we go. Here we go. Let's focus because I feel some anxiety about this stuff. So let's fix that. This is just one example, but it's a good example because it's using all the variables. It's using delta H, delta S, delta G, and K. And then down below, there's a bond energy delta H question. That's really good because I just feel like that's something that we may not spend enough time on when we're learning it. So anyways, let's do this. We'll kind of just do it together. I'm not going to give you a whole lot of time to work on it. I'll just give you a minute to think about it, and then we'll go over it. So they give you this reaction, and sometimes they'll give you an equilibrium reaction, which usually is how it works. But anyways, following reaction and synthesis reaction, there's your delta H, there's your delta S. What is the value of Gibbs free energy, delta G? Now, don't let them 298 and then don't let that freak you out. It just means standard conditions. That's all this means. So the temperature is 298 at this. Not standard, sorry. Standard's 273, normal. Normal is 298. So delta G equals delta H minus T delta S. That's on your equation sheet. You don't need to remember or memorize that. So if they give us delta H and they give us delta S, we know it's 298. We just plug it in and solve for delta G. So part A is pretty easy. You just need to remember to use this, and it's on your equation sheet. But what's one pitfall some students might make? It's not as easy as taking those numbers and plugging them in. It's almost that easy.
They don't convert the units.
Units, right. Either make this into joules or this into kilojoules. I, for some reason, just seem to rather make that into kilojoules. That's just how I do it. It really doesn't matter. Delta G usually, like if you look online or in the back of the book, it's in kilojoules per mole. That's probably why I do it, but it doesn't really matter. So I'm going to do that negative 264 minus 298 times negative 0.278. All right, so remember this whole delta G is based on these two terms. When I say two terms, I mean T delta S is one term and delta H is another. That's how I kind of teach it and how I explain it. So someone do this for us with a calculator or a few of you. So this is negative 264. This term is going to be bigger than 264, so it's going to be negative or positive. I would expect this to be positive, unless I'm not thinking clearly right now. Well, what's 298 times 0.278? Let's write that down. What's 298 times 0.278?
I got negative 181.15 for the whole thing.
It's gotta be negative for that.
Because that's gonna be a
It's a
small
0.2.
positive number. Yeah, you just
Oh yeah, I'm sorry. Yeah.
Negative
Yeah.
small.
I'm not thinking clearly. You're right. All right. So what did we get? What's the final answer?
Negative 181.156.
Negative 181.6. We'll say. Kilojoules per mole. Someone else confirm that?
0.156.
Oh, so 0.2. All right. Okay. So just keep the signs. So it's negative 264 minus whatever that negative is there, and you're telling me this is going to be a smaller term here, so obviously that's negative. Okay, yeah, that makes sense. So, that's it. What does that mean, Liz?
That it's favorable.
Thermodynamically favorable, right? The bigger the negative, the more thermodynamically favorable. How do we determine B, the temperature at which K is 1. What's K equals 1 mean?
It is.
Equilibrium, because K is equal to products over reactants. So when these two are equal, that equals 1. So whenever you have a reaction that is at equilibrium, once your concentrations are the same, it stops it stops reacting. When you finish that thought, that's what we talked about with voltaic cells. Voltaic cells stop running when they reach equilibrium because the concentrations will balance out essentially, and it stop moving, stop working. So anyways, determine the temperature at which the equilibrium constant is 1. Any thoughts on how we do this? Is there an equation with delta G and K in it? I don't know if I have mine handy here. The answer is yes, but I'm waiting for you guys to find it.
Negative RT.
Is that on the equation sheet?
Yep.
Where the heck's the rest of my equation sheet? I thought it was, then I couldn't find it. There it is, yeah. So, on thermodynamics, electrochem, delta G equals negative RT natural log of K. Delta G equals negative RT natural log of K. So, we can plug this in for delta G, or we can, remember now, so now we're dealing with R, which is joules. So this is not 0.0821, it's 8.314, which is in joules. So we either have to make this one into kilojoules or this one into joules. Again, I tend to move that one, so it's negative 181.2 equals negative 0.008314. Yeah. Times T, that's what we're solving for, and what's the natural log of 1?
0.
Natural log of 1 is 0. So if we plug in 1 for K, all of this goes away. Okay, so how does this help? Determine the temperature at which equilibrium constant K is equal to 1. I want you to have some thoughts here. So when delta G is negative, what does that mean? Thermodynamically favorable. What does that mean? Favors forward, the products. What if it's positive? Right. What if it's 0? Then it's at equilibrium. So if delta G is 0, it's at equilibrium, which is when K is equal to 1. So like if K is 1, this whole thing becomes 0 and delta G equals 0. Right? So forget this number for a second. If this is 1, everybody's 0, delta G is 0. So that's my hint. So how do we figure out a temperature?
It's 298. It's already at equilibrium.
If delta G isn't 0 and it's at 298.
So you plug in delta G 0 for the other.
So you want to plug in delta G0 here. And then what? Solve for T? So you want to do equals negative 264 minus T times negative 0.278. You want to solve for T.
Is that right?
Let's find out. So how do you want to solve for T?
Add 264.
You want to add this over here? So 264 equals negative T times negative 0.278.
Divide by positive.
Divide by positive 2.78? We gotta divide by the same
You
thing, right?
divide by a maybe, and then you divide by a
Then you
negative.
divide by negative 1.
Yes.
Divide
Okay, the number's still gonna be the same. We can worry about the signs later. So what's that? What's 264
Just
divided
skip
by
this step.
0.278?
949.6.
940.
9.6.
That equals negative T, but that's negative, so it's positive, is what we're saying? So temperature is 946 K. So at 949, 950 K-ish, then delta G would be 0, right?
Yes.
So then K should equal 1. Yes, I agree with you. I'll check the answer key in a second. That's what I would do. Okay? So this equation is where my mind immediately went, but then I realized, as soon as even Ben said it, I was like, oh, well, this whole thing is 0. That means at equilibrium, that's 0, so K is 1, that's got to be 0. So then, it's good that I did that, because any combination of these two is where they're going to go with equilibrium questions. In this case, that was only useful to remind us, oh, delta G is 0 at equilibrium. Now you plug 0 in here, solve for a new temperature. So yes, I've done this problem before. I'm almost positive it's 950 is on the answer key, so I think we're right. But we can double check. I'll look while you're messing around with part C. So part C, calculate standard enthalpy change, so delta H, that occurs when 0.256 moles of NF3 is formed from N2 and F2 at 1 ATM and 298. So solve for delta H from 0.256 moles. Remember, delta H is kilojoules per mole. So we have to think about that. Let me find this key so we can check ourselves. Of course, I don't have the answers, but I know that's right. Alright, whatever, wasting time. Yeah, I mean, that's right. I know that's how you do it. I always like to check the answers. So just back to this one quick. At equilibrium, K is 1, delta G is 0. What about E cell? That's the other one they talk about. When is E cell favoring products? Is it positive or negative? Positive. E cell's positive, you're favoring products. Negative, it's going the wrong way, not thermodynamically favorable. When is E cell, when is it at equilibrium? Yeah, when batteries stop producing voltage, because E cell is the voltage, 0, that means it's not working. That means it's at equilibrium and it stops. So why am I going over that? The 3 things you need to remember to give yourself a fighting chance on any equilibrium question: E cell 0, delta G 0, K 1. Those 3 are at equilibrium. Negative delta G, you're going to the right. Positive delta G, going to the left. Now negative means thermodynamically favorable. So they're just, in general, in chemistry, when you say thermodynamically favorable, it means products. You're going towards products. That's positive E cell. That's the same thing as negative delta G. And K, the bigger it is, right? Look at this equation. The bigger K is, the more negative that is. So the more, or the further above 1, we'll say, larger than 1, that's better, and less than 1 would not work out. Right? That's the opposite. Thermodynamically not favorable. All right. So we'll put that one to bed here, because I can't find the answer key. Any thoughts on part C? Didn't they already give us the delta H? Yeah, they did. So the formation of this is that. How's this question different? Right. How many moles? What's going on over here? How many moles are being formed in that reaction? 2. So when you form 2 moles of NF3, that's how many kilojoules per mole are being released. We don't have 2 moles of that. How many moles do we have?
1, 2, 3.
So it's a proportion, 1, 2, 5, 6. If 2 mole, again, I don't have the answer key, but this one we can figure out pretty straightforward. If 2 moles releases this much, 0.256 releases how much? All right, so you guys can all do that. That's not something we need to spend a lot of time on, but it seems way more complicated than it is, because they're giving you, why are they giving you the ATM and the temperature? I'll answer that, don't go away. They're doing that so you can use the number on top. That's why they're doing it. So they're telling you this because now you can use this because this is under the same conditions. It's going to be less, right? Smaller number. You're decreasing it significantly. It should be like a quarter of that number, actually, right? No, more than that. Negative what?
33.
Yeah, yep. Again, I don't have the answer, but I've done this so many times, you'd think I would have the answer, but I know I have the answer somewhere. All right. So is this helping, Liz, and whoever else was talking? When you use these, just remember to calculate these two on their own. If it's heat of formation, it's products minus reactants. If it's an overall reaction like this, for example, and they give you the heat of formation of this and this and this, these would be 0 because they're elements, and this would be whatever number it would be times 2. So products minus reactants multiplied by their coefficient, that's how you get that. Same thing with this, and that's if they give you the individual values, and that's kind of what the bottom here is doing, sort of. It says enthalpy change in a chemical reaction is the difference in energy, difference between energy absorbed in breaking bonds in reactants and energy released by bond formation or product. So if we're using heat of formation, again, if you get heat of formation energies, your delta H would be the heat of formation of the products minus the reactants heat of formation, and then you would multiply it by the coefficient. So that's heat of formation. That's the energy required to form something. This is different. This is bond energy, and we talked about this the other day. If you're using bond energy, how do you find the delta H? Bonds broken minus formed. B before F is how I always remember in the alphabet. B comes first, broken formed. So broken minus formed, reactants minus products. Because you break reactant bonds, reform new bonds for products. So if you don't remember this, you can't answer this question. All right, so that's important to remember. And I guess, Skylar, that's I can write that on my list. That's sort of an equation that isn't on your equation sheet. At least I don't think so.
Have you started the list?
Yeah. Yeah, it's not on there. I'll add it to the list. Actually, I can put all those on there. It's on.
Oh, nice.
Miss Snyder came to me and was asking for like a good workout, and I gave it to her on like a ripped up piece of it. It was like a little tiny thing I scribbled on. I'm like, here you go. She's like, are you serious? I'm like, that's how I do things. Sometimes that's all you have is paper towels, right?
You just stack paper right there, the same.
Literally go to the recycling.
I'm just gonna do it.
But you have to go to the back of your room and get a paper towel.
No, I was standing there when she was talking.
He's like, oh, I can make the list on this. Just go to my own.
All right, so let's go.
My bathroom has me trying things up.
Try this.
So they might call this bond energy, bond enthalpy. It's the same thing. Basically, when you form an N triple bond here, it releases this much, but you need that much to break it, and it's the same for all of them. So you guys need to, here I'll write the reaction down. It was N2 plus F2 yields 2 NF3. 3 of those. Yeah, there's the reaction. Okay, this is really good that we're doing this. This is good review problem. I thought I had another one somewhere. There it is. Alright, so we need to know the bond enthalpy. And remember, energy and enthalpy, the only difference really is energy is just joules or kilojoules, enthalpy is joules or kilojoules per mole. I've said that so many times, I really hope you guys remember that. Okay, so this is 1 N triple bonded to an N. This is 3 F's bonded to each other. And this is 2 NF3s. This is important to understand because now you can kind of add up all their energies and do this broken minus formed. So we know the overall delta H, right? It's up on the top. This is why projecting is annoying, why Skylar doesn't like it, I know. The delta H they gave us is negative 264. So the delta H is negative 264 kilojoules. That's the overall. That was at the top of the page, they gave it to you. So this is going to be equal to bonds broken minus bonds formed. So go ahead, I want to give you, it's worth spending some time, see if you can come up with it here. So I'll just kind of set it up a little bit here. So 264 equals, this is going to be your bonds broken minus bonds formed. So I laid it out for you, I kind of did it for you, that's okay, we're reviewing. You have 1 triple bond between the N, 3 single bond F's, and then you have 6 NF bonds, right? 1, 2, 3, 4, 5, 6. So, I'll stop talking. Let's see what you guys come up with here. Bonds broken minus bonds formed. I really wish I had the answer for this one, but we'll just go over it. Something weird going on. There we go. That was weird. My laptop went to sleep. What's going on? Units in thermochemical calculation.
I did the same exact thing. I'm just doing this.
Here we go.
No, I felt like 200.
What number is this? 2007. This will make life a lot easier.
1632.
There she is. Yeah, 950K. What'd you guys get for this one? The Delta H 33 something? Yeah, good. We got those. Okay. Oh, did I miss a question?
Yeah, you missed the.
Oh yeah. How many bonds are formed when two molecules? 6. 6.
Oh.
All right. Now, if you make a mistake, I bet I know this is kind of a lot of not a lot of work, but you got to keep track of things. If you make a mistake, it's probably going to be here. This number is a third of what that's going to be. Like if you make this all one number, you have to divide it by 3 to get the answer because it's 3 times, right? So it's going to be there's one N triple bond, so whatever that is, 1 times that 3 times the FF bond, all of that minus 2 times the NF. Actually,
Isn't it? Do you multiply? Isn't it adding between the N and the F?
right? So, but there's 3 of them, so it's
No,
adding and
one should
multiplying.
Add the
The
N
nitrogen
bond.
and two.
Oh yeah. Yes, adding. Sorry, yes. And then this one is going to be 6 times the NF. Right. So that's kind of the setup. You have 1 triple bonded N, 3 Fs. What is that? What is this? You add them, subtract 6 times, and that's how you get your answer. What'd you guys get?
140.
Yeah, they have 141. Positive though. Positive.
I had 1 point.
Because these are so when you form this, it releases that to break. So just to be clear, bond enthalpy, when they have a chart, it's going to be all positive numbers. That's the energy needed to break those. That's what that means. So yeah, this would be 946. This would be X. This would be 272. So that times 6, add it to that. And then you can subtract 946, divide by 3. You guys can all do the math. I know you can. So 141, that's how we would set it up. Okay. That was good. We reviewed a lot of good stuff right there. Alright. Okay. So there's that. Now, what else did you ask me, Skylar? You said something about something. Rate laws. Oh, it just so happens I have this beauty right here. Would you look at that? Is right. All right. So there we go. All right. There it is. This is great. Right on cue. All right. So you got trial 1, trial 2, trial 3. They give you. Oh, here. Let me. Again, this is the problem with projecting. There's the overall reaction. Acidic medium, whenever you have a redox, potassium permanganate, we talked about that this year a little bit here at the end. So you're reacting these two primarily. The Mn is going from a +7 down to a +3. That means it's gaining 4 electrons. The Cl is going from -1 to 0, so it's losing an electron. So each Cl is losing 1. Therefore, you have 4 zeros. There's your 4 electrons. They go to Mn and it goes down to a +3. So I'm just kind of giving you the overview there. That's how I want you to approach redox electrochem questions. Figure out the charges. Figure out the charges. You can figure out moles of electrons that way, and then that's going to help. All right. So you don't really need all that to answer this stuff. So you have your 3 trials. Notice the concentration of H+ stays the same because that's the medium. Using your information, determine the order with respect to each of the following. Cl-, MnO4-. So how do we do this? I talked about it today a little bit. Anybody? Anybody got anything for me? Alright, find 2 reactions, 2 trials where one's held constant and the other one isn't. So if you look at 1 and 2, who's constant and who's changing? Constant. So the rate is changing, it's going up. This concentration is changing as well. This concentration is not. So we take trial 2 and divide it by trial 1. So if you take 2.03 times 10 to the negative 7, always take the bigger number, divide it in terms of the rate. Always take the bigger and divide it by the smaller. So that's going to help you out here. So 2.03 times 10 to the negative 7 divided by 2.25 equals, and now this would be rate equals K times the concentration of Cl minus times the concentration of MnO4 minus. I'm not going to write it all out because that's a waste of time. This is the same number, so that goes away. K is a constant, that goes away. So really, all we're doing is taking 0.0312 divided by 0.0104. So divide this first. Someone tell me what that number is, even though I'm looking at it. Should be 3. That number's 3 times bigger than that, according to the answer key. 3 equals, and now remember, this is raised to a power. That's what we're trying to figure out. Maybe you didn't remember, but that's what we're trying, that's the rate law. It's going to be rate equals K times Cl minus X, and then O4 minus to the Y. We're trying to figure out X. So what's 0.0312 divided by 0.0104? This is 3, right? Or no? Yes? Or is it the other way around? No.
I got 9.
This
I got
is 9, that's 3.
I thought I was
Sorry,
stupid
Tristan.
or something.
I did it backwards.
Yeah.
I
I
did
got
that
9.
one.
Yeah, sorry. I might have said it one way, but I was thinking the other way. So I'm sorry.
What's that one?
Yeah, my fault.
Nice.
My
You
fault.
wanted you to
So
say
this divided by this is 9. This divided by this is 3. Everybody with me? So what's X? 2. So this is second order. So in our rate law, this is 2. When the rate is changed by, we'll say a factor of 9, is changed by a factor of 3, that's a change of the coefficient, not coefficient, exponent of 2. So anyways, that makes it second order. Because whatever that exponent is the order. 0, 0, 1, 1, 2, 2, 3, 3. Okay, you do the same thing for MnO4 minus. So trials 2 and 3, we would do 1.0, no. We do 2 and 3. Because that number's bigger than that number. 2.03, right? Yeah. 1.02 equals, and that's bigger than that, 0.004 divided by 0.002. So when you do that, I'll just save you the math, it's 2 and 2. So this is 2, this is 2 raised to the y, so this is first order. That's how you do rate reaction order if they give you a chart. They can give you a graph, and I'll go through those, I don't have time right now, but we'll go through the first order graph, second order graph, you know, what that looks like. Does that help a little bit? Okay.